the stator and welded to the laminations. And thus, multiple fault loops are formed between failure point and key bars, as shown in the pink color around the stator core. And these fault loops are not these fault loops are not perpendicular to the yoke field. The combination of all these factors results in the smoother pattern in the graph, as shown in the third graph. Okay. The advantages of the proposed test method are the most important advantage is the fault detection and classification capability. EC implementation is another benefit, since no extra sensors and computational hardware is required. The proposed technique can detect faults with high precision, since the test signal can be optimized for maximum sensitivity. And therefore, the difficult to detect faults can be diagnosed automatically and remotely under noise-free condition. And now I will show my experimental results. Before that, I will briefly introduce my experimental setup. And the proposed technique was validated on 6-pole wound-rotor induction motors with emulated faults. The defective contact and shorted turn faults were introduced in the first machine. In the top, 4 contactors emulated by connecting a series resistor to one phase, and which is about 11% increase. And shorting adjacent turns in the random winding is a very difficult task. Therefore, the same number of coils were added to each phase to control fault level from 0 to 3 shorted turns, as shown in the circuit diagram in the top second column. The stator core insulation failure was tested on the second machine in the bottom, as shown in the bottom. And fault was introduced by welding, as shown in the thermal image. A custom volt inverter was used to inject full setting fields with different electrical angles. The rotor voltage and current were measured with commercial sensors and data acquisition systems with a sampling rate of 10 kHz. Then values of REQ and XEQ were calculated and plotted while increasing field angle in discrete steps. Now let's see the experimental results as shown in plot. The plot for the defective contact is shown. The blue line is healthy motor, and the red one is faulty, a defective fault in the motor. The sinusoidal pattern is evident in REQ, and no change in XEQ except for negligible murmuration, as you can see. Next plot is for rotor turn fault with different excitation frequencies, 60 and 500 Hz. It also shows different fault levels, 1 and 3 shorter turns. And the sinusoidal increase in REQ, decrease in XEQ is clear, as you can see. And more importantly, the maximum change is significantly increased with the frequency. This means sensitivity also increased with excitation frequency, which is an advantage of the proposed technique. The plots for stator core insulation failure with 2 fault levels are shown. The result obtained with 500 Hz excitation shows increase in REQ and decrease in XEQ, similarly. However, as I mentioned many times, the pattern is not sinusoidal. It's much more smoother compared to the shorter rotor turn, because there is many fault loops between the key bars and the failure point. So, experimental result validates the prediction from the equivalent circuit analysis. And the percentage change in REQ and XEQ can be plotted and used for classification of 3 faults. In the case of defective contact, the graph shows sinusoidal increase only in REQ. Almost no change in XEQ, as you can see in the first graph. The next graph for rotor turn fault shows clear sinusoidal increase in REQ and decrease in XEQ. And the last graph for stator core fault shows non-sinusoidal pattern, as you can see. The unique and smoother pattern makes it easy to distinguish tree faults. This also enables non-invasive condition monitoring of stator core insulation. So here's my conclusion. And new offline test method that uses rotor side inverter was proposed and verified in this work. Three different types of faults were unambiguously detected and classified. And advantages of the proposed test method are the sensitivity can be enhanced with excitation frequency. The proposed method can be easily adapted without extra hardware for aftermarket, remote, and noise-free detection. Therefore, a new test method is expected to improve the reliability of wind turbine with reduced maintenance cost. And this is the reference list I used in the presentation. And here's the end of my presentation. Thank you for your attention. If you have any question, please feel free to ask. Thank you.
Thank you so much. Thank you very much presentation. And the conference committee, do you have any question?
Yes.
Sign off.
Bямbasүrэн, thank you for your presentation. It's an interesting study, I think. Yeah, I have several questions. First, you've mentioned that you don't need any additional equipments to carry out this fault detection setup, but you have to create that pulsating current and you have to censor it back, the results. So I think you have some additional equipments. What do you say on that?
Yeah, okay, it's a very interesting question. Thank you for the question. And as I mentioned, the only thing we need to conduct this test in the DFIG system is the programming of the inverter. That algorithm can be added in the inverter system. So during the standby, when the DFIG is not working, when the DFIG is not working, inverter can be inject signal to the rotor, and then that pulsating field will be created, and from that we can measure the voltage and currents by using the already existing measurement instruments in the DFIG system, like CTs or voltage meters. So from that measurement data, we can calculate equivalent impedance. Then we can